this chapter we talk about the statistics. Statistic is the function of the observation x1 and x2. Suppose x equal x1 to xn is observed value of the samples of x1 and xn. Tx is a function of this value, and we use Tx to estimate the parameter theta or find two testing hypotheses by the theta. So the statistic Tx is the importance, and we have some difference statistics. For example, sufficient statistic, ancillary statistic, complete statistics, and there are some relation between this type of statistics. So we work and study about these different kind of the statistics. Now, every statistics summarize the data. In fact, the samples include all information about a parameter theta and maybe another information. Therefore, when you use the Tx, we used some part of this information. We want to select a statistic Tx, which is summarize the information in the samples but don't miss any information about the parameter. This statistics is called sufficient statistics. So the statistic Tx is sufficient statistics is summarize the data without discard any information about the unknown parameter. If you want to give the information about a theta, we can use Tx instead of samples x. Now we give the definition of the sufficient statistics. A statistic x is a sufficient statistic for theta if the conditional distribution of x given the value of Tx does not depend on theta. So if we know the value of Tx, we don't need the sample x, which is the reason to give this information. For example, let x1 and x2 be independent person with the common expected value theta. The joint distribution of x1 and x2 is given by product of their probability, because they are independent person. We can write product of the persons for x1 and x2, and we give this probability. We then calculated the conditional distribution of x1 and x2 given x1 plus x2 equal by s. which is this probability. As we know, it is the probability equal the probability x1 and x2 and s divided by probability of s equal s. We know distribution of x1 plus x2 is a Poisson with expectation 2 theta. So we can write this form as probability, and we can omit it common factor from numerator and denominators. For example, e power minus 2 theta and e power minus 2 theta is deleted or omitted, or theta s and theta s against deleted, and we obtain this conditional probability. If you look of that, does not dependent on the parameter theta, so s x1 and x2 equal x1 plus x2 is a sufficient statistics. Or the different definition of the sufficient statistic is a difficult way to find a sufficient statistics, because we must just statistic tx and check the conditional distribution x given sufficient statistics and find this condition distribution does not depend on theta, but there are a theorem as a factorization theorem to give a way to find sufficient statistic very easily. Let p x equal x equal fx theta or fx1 to xn theta denote the joint PDF or PMF sample x1 and xn. A necessary and a sufficient condition that tx be sufficient for theta is there exists a factorization fx theta equal g theta tx productive in hx, when the first factor maybe depend on theta but depend on x through tx, and the second factor is only function of x and independent of theta. So this says if can write this factorization, tx is sufficient, and if tx is sufficient we have this factorization. So it's a way to find sufficient statistics. The proof is given for discrete distribution. First, suppose tx is sufficient statistics. By the definition of sufficient statistic, probability x equal x conditional tx equal t or co x to t is independent of theta. This is the definition of the sufficient statistic. So we have probability of x equal x equal is a probability of x equal x and tx equal tx, and we can use of product probability to write this form. The probability of Tx equal T in the probability x equal x, condition Tx equal T, and we have this for we can define probability Tx equal T a g theta Tx, and this part is independent of theta is called Hx. This is when the fx theta is not equal 0. If fx theta equals 0, we choose Hx equals 0, and we have this factorization. So in the second part, suppose we have this factorization, we should show that Tx is sufficient. In fact, we show that probability of x equal x, conditional Tx equal T is independent of theta. Probability of x equal T is summation of p theta x. When the Tx is T, we can write and use this factorization here and find that. Now the probability of x equal x, condition T equals 0 if Tx not equal to T, and is the probability of the fx equal x is that one, and divided by probability of Tx equal T, and we can omit the common factor from numerator and denominator, and we have this result, which is independent of the T. So Tx is sufficient statistic by definition. In the next example, we find sufficient statistic by the theorem 2.1, factorization theorem. Let x1 to xn be independent identical distribution from a binary distribution. So this is a density function, and fx conditional theta is product of fxi, because independency of x1 to xn, and if we replace it fxi by this, we find this production, and you have that. So we can take hx equal 1 and gtx theta equal that. There t equals summation I 1 to n xi is sufficient statistics for theta. Next example, let x1 to xn be a random sample from a normal distribution. So theta have two dimension, mu and sigma do, and we can write the probability of x1 to xn. Because of dependency, we have this production, replace the density of function of the normal, and this part is fixed value when you calculated the product of that is the fixed value powered by n, and have this one. We can write this part by that, and s equals summation xi, and summation xi power 2 is sufficient for statistics for theta. Next example. Let x1 to xn be a random samples from a uniform distribution theta 1 and theta 2. This is the density of uniform distribution, and can write density function as this one by using the indicator function ia x. ia x is by definition is equal 1 if x belongs to a, and otherwise the value of ia x equals 0. So we have x1 less than xn less than theta 2, and theta 1 is less than x1. When x1 is the minimum of x1 to xn, and xn is maximum x1 to xn, the order statistics. So similar other example, we can write fx theta equal to product of fxi theta, and we put the density function here. This part is fixed, does not depend to I, and so the product of the one is 1 theta 1 minus theta 2 power n, and we have this production. If you look of that, I xi, I theta 1 theta 2 xi equal 1 or 0. The product is 1 is if all value of I theta 1 theta 2 xi equal to 1, and 0 if one of them of 0. So when this product is 1, if x1 and xn are between theta 1 and theta 2, if x1 and x2 between theta 1 and theta 2, because the minimum and maximum data is between theta 1 and theta 2, all of xi between theta 1 and theta 2, and all of ia theta 1 theta 2 xi equal 1, and this product is 1. Otherwise this product equal 0. So we have this part is fixed, and you can write these inequalities by that one. The x1 is between theta 1 and infinity, and xn is between minus infinity to theta 2. So hx is equal 1, we can get hx equal 1, and gt is that. So tx equal x1 and xn is a sufficient statistic for theta. In the particular, if theta 1 is equal alpha is known, and theta 2 is theta is unknown. In this case, this part is a non-value is hx, and 2 part that is gt, and we can see xn is a sufficient statistic for theta. Similarly, if theta 2 is beta is known and theta 1 is theta is unknown, this part you can take, this is a known value, and take hx is not depend of the parameters, and this is gt, and in this case x1 is a sufficient statistics for theta. In next section we look at the function of the sufficient statistics. Suppose x1 to xn is a random samples, and theta is theta 1 to theta r is the parameters, and t equal to 1 to tm is the statistics, is m-dimensional statistics. We have a lemma 2.1, let phi is Rm to Rm be 1 to 1, so the inverse phi inverse 1 exists if t is sufficient for theta, then t tilde equal phi t is sufficient for theta, and t is sufficient for psi theta, where psi is a 1-to-1 function of theta. This lemma is important because give a way from find more sufficient statistic for parameter theta. So if t is sufficient for theta, any 1-to-1 function of t is sufficient for theta, but t is sufficient for any 1-to-1 function of theta. So if we have a sufficient statistic, we have a family of sufficient statistic, not only one sufficient statistic. Look at a next example. Let x1 to xn be a random sample from a beta distribution. So the density function of beta is that, and the f x1 to xn, the joint distribution x1 of xn, given by this product. So this part is independent of I and is powered by n. This part is I equal 1 to n xi power alpha minus 1, and this one is product of 1 minus xi with power by beta minus 1. So we have product of xj and 1 minus xj sufficient for theta. So every 1-to-1 function of t is sufficient for theta, minus log ln t is a 1-to-1 function, so minus ln product xj and minus ln product of 1 minus xj is sufficient for theta. And in particular, if theta summation minus summation xi ln xj sufficient for theta, when beta is known, or minus summation ln 1 minus xi is summation for theta equal beta is alpha is known. In the next part, we talk about the minimal sufficient statistics. As we discussed here, there are several sufficient statistics. Which one we should select it to make the statistical inference? Reality, that one which make data summarize more than others. A sufficient statistic is summarize the data more than other sufficient statistics is called minimal sufficient statistics. Before giving the definition of minimal sufficient statistics, look at this example. Let x1 to xn be identical independent identical distribution from normal 0 and sigma square. T1x equal x1 to xn, the sample sufficient. T2 is also sufficient, but as we know, this is n-dimensional statistics, and T2 is against the n-dimension, but just only positive value is considered. T2 is a two-dimensional sufficient statistics, and T4 is x1 power 2 square xn is all sufficient statistics. T1, T2 to T4 all is sufficient statistics, but when the index increase, the dimension of the data decrease, or the data are much summarized. So the last one is a minimal sufficient statistics. The definition is given by that. A sufficient statistic to star x is called the minimal sufficient statistic if T star x is a function of any other sufficient statistics. So T star x minimal sufficient statistics if a T star is function of other sufficient statistics. To see that, T star is a function of Tx, we should show that if Tx equal Ty, then T star x equal T star y. And if you look at the partition set introduced by the T it is enough to show that the BI is a subset of AI or any partition set of T star X include some partition sets from partition introduced by Tx. The way to find the minimal sufficiency, let's say, will be in the next talk.